Our next topic is filter realizations. Now, basically speaking, realization of a filter essentially means that the representation of a filter through a block diagram. So, just represent any transfer function in the Z domain by using a block diagram can be termed as filter realizations. Now, in order to realize a filter, typically some standard symbols are found. So let us look at those symbols. First of all, there is the adder block. So if x of n is our given signal that goes to our adder block, that will look something like this, and w of n is another signal, discrete of course, both of the signals coming to the adder block, then the signal getting out, y of n, will be equal to x of n plus w of n. So this is the function of an adder block. Similarly, like the adder block, there is the multiplier, which works if x of n is a signal, it goes to y of n, and in doing so it finds a multiplier, that is a, then y of n will be equal to a x of n. So the multiplier in most of the cases that we will find is a scalar multiplier. That means this sort of multiplier will do nothing but multiply a constant coefficient or a scalar value to our given signal. If we want to multiply two signals together, then we may use a signal multiplier block or a different multiplier block. We are not concerned with that at this moment. Then there is the most important unit delay block. So for that, let us revert back to Z transform. If x of n is having a Z transform of x of z, then it is known to us all, x of n minus 1 will have a Z transform of Z inverse x of z. Similarly, x of n minus 2 will have Z inverse 2 x of z. So, simply speaking, a unit delay block will consist of Z inverse 1 operators. So, if x of n is our given signal, then we give it a unit delay block, then y is equal to x of n minus 1. So if we want to find out the second delay, that means delay by two samples, what we are going to do is use two different delay blocks, Z inverse 1, Z inverse 1. Here the signal will be n minus 1, and here it will be y of n will be equal to x of n minus 2. Under no circumstances you can use this sort of blocks, that is Z inverse 2, in order to make two delays. So what I'm trying to say is that how many numbers of delay you want to make, the same number of delay blocks, or rather I should say unit delay blocks, you must use in order to illustrate the block diagram. So the fourth symbol, which is the pick of node is nothing but to use to beautify our block diagram. Say we are giving a signal x of n that goes along this line, and if we want to use x of n in a different block, what we can do is get x of n like this to a different block, or what we can use is a pick of node. So if we take a pick of node at this point and bring out x of n like this will be x of n, and from this pick of node this will also be x of n. Just splitting x of n so that it can be used to two different blocks. Something quite identical to parallel circuit. That means using one source, if we want to connect two different types of bulbs, we may use this sort of pick of node representation. So these are our 4 cardinal blocks that we'll be using in the filter realization. Now, broadly speaking, there are 4 different types of filter realization which can be used to illustrate not only filters but any sort of causal LTI systems. They are namely the direct form 1, direct form 2, cascade form, and the parallel form. So in our filter realizations, we shall be discussing all these forms of realizations. Now, there are 2 different types of systems. Say these are specific type of systems. There are all zero system, which is a system not having any poles, and the transfer function of it will look something like this: h of z b0 plus b1 z inverse b2 z inverse 2 bm z inverse m. So this is a all zero system. So see, there is no denominator and hence there is no poles. And the second type of system, as you have guessed, is an all pole system. This type of system will have no zeros and hence will have the transfer function h of z, which is equal to 1 over 1 plus a z inverse to z inverse 2 Now, in practical cases, any system can be all zero system, or it may be all pole system. Rather, what we are concerned, or in most of the cases, the system occurs as a combination of all pole or all zero system. That means the system has both the poles and both the zeros. Now, if you look upon closely to the all zero system, there is no denominator or pole. So hence, this system is nothing but a form of FIR filter, and this system is a form of IIR filter, although IIR filter can have zero as well. So these are the basics of the filter realization. Now let us go and realize some filters through some mathematical examples. So the first example is to determine the direct form 1 and direct form 2 for the system with the difference equation ten y of n is equal to minus y n minus 1 y of n minus 2 30x of n minus 1 6x of minus 2. So let us go to the solution. The first task is to determine the transfer function in the z domain. So in order to do that, what we are going to do is first divide both sides of the equations by 10, so that in the left hand side we have a pure y of n. That will be our first task. Whatever may be the value over here, whether it comes fractional or whatever number coefficients, our task is to get a pure y of n without any coefficients, or in other words a coefficient of 1 in the system. This will be equal to minus 0.1 y of n minus 1 plus 0.2 y of n minus 2 is 3x of n plus 3.6x of n minus 1 plus 0.6 x of n minus 2. Now what we are going to do is apply the z transform or the z transform. Y of n will become y of z minus 0.1 y of z times the delay z inverse 0.2 y of z inverse 2 3 x of z 0.6 z inverse x of z inverse 2 x of z. Taking y of z as a common factor, we get 1 plus 0.1 z inverse plus 0.2 z inverse 2. The right hand side, taking x of z as the common factor, be 3 plus 0.6 z inverse 2. Now from here we can easily devise our transfer function. H of z, which equals y of z over x of z, will be equal to 3 plus 3.6 z inverse 0.6 z squared 1 plus 0.1 z inverse minus 0.2 z, this is inverse 2, this is negative squared. So we found out our transfer function. Now let us construct the direct form 2 first. So direct form 2. So first of all, we will be having a signal x of n, and obviously we will have an output y of n. The second task is to determine how many number of delays we need, and that is given by the maximum number of negative powers either in the numerator or in the denominator. So if there was x z raised to minus 3 present in the numerator, the highest number of delays we'll be requiring is 3, and consequently if this was z raised to minus 2 and this was z raised to minus 3, the highest number of delay will also be 3. In the case both are same, we may take any one of the value. That means what I am trying to say is that all we are concerned is with the highest power of the polynomial either in the numerator or denominator. So in the numerator the highest power is -2, in the denominator it is also -2. So we shall be requiring 2 delays. So give a point over here or a pick off node. So this is our first delay, and this will be our second delay. So now what we are going to do is that if you take y of n to be pure, that is having a coefficient 1, there will always occur a 1 at the denominator. So the denominator polynomial will always start with 1, and this one will go directly to the pick off node. So there will be a multiplier of 1. See, these coefficients are nothing but the multiplier values. Now in the direct form 2, in the left hand side we shall plot the poles. That is, we shall devise an all pole system in the left hand side and all zero system in the right hand side. So z inverse 1, so this is z inverse 1 over here, and this will be z inverse 2. So z inverse 1 will come over here, and it has a multiplier of 0.1. Now since the signal is going back in case of poles, so there will be a multiplier of 0.1, but there will be a negative sign. So you may always remember that the poles of the system will be negated. So this is an adder, this is also an adder. So this is our first portion. Point to be noted, a signal or an adder block can handle 2 signals at a time. So simply you cannot join these more than 2 signals over here. Now why have we given an adder over here? Because another signal will come from this point and meet at this adder, and for that reason we are using an adder block over here. So you must be careful about that. Now z inverse 2 has a coefficient of 0.2, so this will come. They are in no higher terms than z inverse 2, so no more adder blocks are required. This will come as it is. Obviously this will be having a multiplier of, here it is minus 0.2, so this will be plus 0.2. So this is our first portion done. In the second portion, all the signals will go to the output side. No signal will revert back to the input side. So 3 doesn't have a coefficient, doesn't have any delays with it. So 3 will go to y of z, y of n as it is. So there is a multiplier of 3. This is our y of n. Z inverse 1 is having a multiplier of 3.6. So put a pick of node, bring this 3.6. Since the direction flow is towards the output, so we need not negate the coefficient in this part. There will be an adder block since there is another term after Z inverse 1, and this will go directly to the output. Similarly, this is Z inverse 1. At this point it will be Z inverse 2, which is having a coefficient of 0.6. be 0.6. So basically this is our representation of direct form 2. And our this portion, let me mark it, will be an all pole system, and this portion is over here will be an all zero system. So if you can draw direct from 2, direct from 1 is completely easy. Direct from 1 essentially comes from direct from 2, where we represent the all pole all zero system in the left part and all pole system in the right part. So what we are going to do is similarly for direct from 1, there will be an x of n. Remember, x of n and y of n will not or never change its position. So take this point and consider it and join it with x of n. So this point is joined over here, and draw the delays as given. Z inverse, Z inverse. So these are our delays, and all this goes to the this summation. So there will be summation, this value will be 3. Here we get another error block, this will be 3.6, and finally from this can connect this to this will be having a value of 0.6. Clear? I hope it is clear. So this is our all zero system represented in the left hand side. What we need to do now is replace the all pole system in the right hand side. So here the first thing we get is an adder. Rather, let us come from this point. So take this point and connect it to y of n. Y of n is connected to this point, and hence the delay Z inverse, Z inverse. Consider this to be your reference point in both the realizations. This is our case. So one will go from a summation. So take a different summation, obviously, because this summation and this summation are not the same thing. So one will go in the direction of y of n. There will be a feedback over here having a value of 0.1, negative 0.1, and there will be another feedback that is having a value of positive 0.2. So this is the all pole system represented in the right hand side. So if that is the case, all we are left with is just connect these two summation or adder block, and this is our required direct form 1 representation. Now it is quite clear from the direct form 1 representation what is the nature of the filter. So if you can recollect the basic discussions on FIR and IIR filter, you see the signal, or rather the filter is having a form of output feedback to get the new output. That is, there is a recursion going at this point and this point as well. Hence, since the filter is dependent on the previous value of the outputs, so we can safely say that the filter that is described over here is nothing but an IIR filter. So this was our direct form 1 and 2. In the next problem, we'll try to see the cascade form and the parallel form.